Hello everyone, we are going to do review here or solve examples for sections 4.1, 4.2 and 4.3. So we are going to start with 4.1 where we just learned about general vector spaces. And what we did mostly in this section is a set of axioms for vector spaces. Remember there are 10 axioms, right? And for a set to make a vector space, it's supposed to satisfy 10 axioms. What I'm going to do, guys, considering that we already kind of had the lecture and you know the theory, I'm going to consider several examples. And the first example actually is going to be a missing part of the proof from lecture. Remember, in the lecture, I was proving a theorem after like axioms. And the theorem sounded like about multiplication of scalars by zero vector or multiplication of vectors by zero scalar. And last part of the theorem was looking like this. Proof. So that's going to be my first example. Proof that if scalar k, scalar multiplication by vector u, is equal to vector 0, then either k equals 0 or u equals 0. So that's going to be the theorem which we'll need to prove. Well, it's part number 4 of actual theorem, right? I proved 3 parts in the previous video, and this is going to be the last part. So what I'm going to do, guys, how I'm going to prove it. First, I'm going to assume, or let's look at this like what we're supposed to prove. And I'm going to see that I have a condition that k equals 0 or u equals 0. But for k, we have kind of two conditions, right? Let's consider that like the statement is like, we don't know it's true or not, but k can be either equals 0 or not equals 0. I'm going to consider the case when k is not equal to 0. What is going to happen? Well, k is a constant, right? It can be equal 0 or not equal 0. Actually, if it equals 0, it's already proved. The theorem is proved already, right? If k equals 0, then like this statement is correct, because if this one is true, then it doesn't matter whether the second part is true, it's still going to be a true statement. So let's consider that k is not equal to 0. So what we can do, guys, we can multiply our statement by 1 over k. So I'm going to multiply 1 over k. Well, because k is not equal to 0, I can divide 1 over k. And that's going to be like, again, scalar multiplication. And u here. And 1 over k, scalar multiplication by 0. Well, what we have over here, we remember that by one of the axioms, we can actually unify this to 1 over k and use just regular multiplication between numbers. What we have over here, guys, we remember that any scalar multiplied by 0 vector is going to be a 0 vector. We proved it in the same theorem. I think that was part 1 probably. So now what we have here, k by 1 over k is going to give me 1, and the cross, not cross product, but product scalar multiplication is equal to 0. What we have? We have 1 multiplied by some vector equals to 0. Well, we know that 1 multiplied by a vector is still kind of vector itself by axioms of like axiom number 10. So we get that vector u is 0. So guys, what we actually proved here, that in case k is not equal to 0, then u must be equal to 0. There is no escape. If this one is not working, then this is working. Now, case analysis. Let's prove b. What is going to happen when k equals to 0? Well, when k equals to 0 means that this statement is already true. Because if k equals to 0, then k equals to 0. And that's going to be true already. So basically, we proved our theorem. In case k equals to 0, we don't really care what is u, because it's just the first part of the statement. If it's true, when statement is or, we remember that is disjunction. And disjunction is true when either both components are true, or one component is true, or another component is true. Disjunction is false only when both are false. Okay, very good. So that was my first example, which was actually part of the proof, right? Let's consider a second example. While talking about vector spaces, let's consider a set of matrices 2 by 2, which is going to have a special form A, 0, 0, B. So actually what we have over here, a set of diagonal matrices. And let's consider plus standard matrix operations, like addition of two matrices or multiplication matrix by a constant. So is this set, is it a vector space? Is it a vector space? Well, to check whether it's a vector space, basically, guys, we're supposed to check vector axioms, right? And we do have axiom number 1, which tells us that sum of two vectors from this vector space is supposed to be also a vector from this vector space. So let's check it. Axiom number 1. So we have A1, 0, 0, B1 plus, and this addition is a matrix addition. So it's not like standard, like a normal addition between numbers, but we remember that when we add matrices, we just add the components, right? A2, 0, B2. So the sum is going to look like A1 plus A2, right? 0, 0, B1 plus B2. So it's going to belong to the same vector space. So if this belongs to this vector space and this belongs to this vector space, the sum is belonging to vector space. Next, so do they commute? Well, we kind of see that addition is going to commute. We are not going to check it. Let's just kind of check, put a check mark for number 3, right? Associative law is working. Looks like it's going to work. We remember for matrices, associative law is working. So very good. Do we have a 0 over here? Yeah. If we set up like A and B equals to 0, we are going to have 0, 0, 0, 0. And this is going to work as our 0 vector, right? Because you add this matrix to any and you are still going to get the matrix itself. So it works, right? Now, do we have a negative? Negative means that like you have a matrix which you add to this one and you get the 0. Yeah. And what is going to be negative? Well, negative of A, 0, 0, B is going to be what? Minus A, 0, 0, minus B. So if you add this one and original matrix, you are going to get 0. So perfect, works. Scalar multiplication. Well, why those axioms are working so good actually? Why? Because all these addition laws are working on matrices already. We already knew that they're working on matrices. Guys, all multiplication laws are going to mostly work on matrices too, just because you multiply matrix by a constant. I'm going to check one. Let's imagine that I multiply matrix by any arbitrary constant, and the matrix looks like A, 0, 0, B. And what I'm going to get? I'm going to get Ka, 0, 0, Kb, right? These two zeros multiplied by K is going to give me 0. So it still belongs to vector space. So it belongs to vector space. And axioms 7, 8, and 9 are going to just work because, like, for matrices, we do have them working. So I'm going to just 7, 8, and 9. We're going to check them. Now, axiom number 10. What is going to be if I multiply 1 by A, 0, 0, B? Are we still going to get the same matrix? Yeah, if we multiply 1 by it, we're still going to get the same matrix. So we just proved that all 10 axioms are satisfied, and that's a vector space. So diagonal matrices of 2 by 2 size are making a vector space. Now let's consider example where probably we don't have vector space. So number 3, let's consider a set of two numbers x and y which satisfy next condition, x greater or equal than 0 and y is greater or equal than 0. So we are considering like all points in the first quadrant and standard operations on R2 and standard operations on R2. Oh, sorry, instead of 2 wrote n actually. Let's fix it. What means set of standard operations on R2? Well, vectors of like with two components. We can multiply them by a number and we can add them, subtract them, do everything. Is this set going to be a vector space? Is it a vector space? Question. Is it a vector space? Well, looks like all math, like, that's addition and scalar multiplication is going to work on this set just because like it's working like on a set like on R2 and we already know that it's working. Well, the only things we want probably to check if we have like 0 suspicious axioms, or if actually it's a set is closed about addition and the set is closed about multiplication. I'm going to start with closure axioms. Oh, sorry guys. So I'm going to start with closure axioms. Sometimes I press something on my notebook and it's giving me different screens. So closure axioms. So imagine that we have two basically x and y are positive numbers. If we have two positive numbers, x1, y1 plus x2, y2, according to our addition standard operations in R2, we are supposed to have x1 plus x2, y1 plus y2, right? Is it going to be a positive number? Yeah, it's going to be a positive number if both x and y are positive. They are going to be positive just because this is positive and this is positive and this is positive and this is positive. So it's kind of closed about addition, right? Is it going to be closed about vector multiplication? This is axiom number 6 by arbitrary constant, arbitrary scalar. Let's write it down. K, x, y is going to be, according to standard operations, it's supposed to be kx and ky, right? Now guys, k is any real number. So it's not necessarily supposed to be positive. It can be, for example, negative. Let's k be equal to -1. What are we going to have? In this case, kxy is going to be equal -x, -y. And these two numbers are going to be negative just because if they were like positive here, or they were belonging to that space, they're going to be negative, and it's not going to belong actually to vector space. So we have axiom number 6 not working. We can try to check other axioms, but normally if I'm not asking you to find all axioms which are not working, but just asking you to find out if it's a vector space or not, it's enough to find one axiom not working. So normally, guys, try to read the question carefully and answer the question, not trying to do always a standard procedure. For example, here I'm asking, is it a vector space? Well, according to not working axiom number 6, it's not a vector space. There are probably other axioms which are not going to work, but I'm not asking you to find them all, right? So if I ask you a question like, okay, find all not working axioms, then I would really like you to check all axioms and find the ones which are not working. Here, we found that this one is not working, you're fine. So we are going to write down not a vector space. And you can write down that axiom number 6 is not working, the closure axioms. Actually, when you test something for vector spaces first, check closure axioms. Because if they are working, then, well, we can move to this addition, multiplication stuff, 0 stuff, negative, and like multiplication by 1. If they're not working in the beginning, well, that makes sense to check the rest. Okay, I think that's all about section 4.1. And I think I'm going to finish this little review and move to section 4.2 in our next video. because it's already like 14 minutes.